Hello everyone. Today we're going to talk about derivatives of inverse functions and logs. So we're going to start with a cool little theorem, look at some examples, and I'll give you some more derivative rules. So we'll start with our theorem. So if f has an interval, we'll call it I, as its domain, and f prime, so the derivative, exists and is never zero on I, this part is important here, because if we get it 0 on I, it's not going to be true, because it's going to have a domain problem. Then f inverse of x is differentiable at every point in its domain. Okay, so that's the first part. It's differentiable at every point in its domain. But more specifically, the value of f inverse prime at a point B in the domain of f prime, sorry, in the domain of f inverse, so in a point B in the domain, is the reciprocal of the value of f prime at the point A equals f inverse of B. Okay, so let's see, what does this mean? So if I take f inverse of, take f inverse, we take the derivative, we're considering this point B. This is the same thing as the reciprocal, so 1 over f prime of f inverse of B. All right, so let's look at an example. So we're going to be able to evaluate basically by taking the derivative and evaluating at a point instead of having to find the inverse of a function. So let's look at an example. All right, so let's say f of x is x squared. We'll say x is greater than 0. So remember, we have to make sure it's never 0 in its domain. And in this case, we know the inverse. Inverse of x squared, trivially, square root of x. Have derivatives. F prime of x equals 2x. And f inverse prime is 1/2 x to the negative 1/2. So we've seen that multiple times. And remember, we can write this as 1 over 2 root x. Okay, so now let's look at this theorem. So we know these derivatives pretty trivially, so we can just see that this theorem is true, and then we'll do an example without finding the derivative. Sorry, without finding the inverse. So if we start with, let's say, f inverse prime of x equals 1 over f prime of f inverse of x. We evaluate this right-hand side. We have 1 over 2 of f inverse of x. And this is 1 over 2 root x. And we just said that was true. If we take the derivative of the inverse, it's the same thing as 1 over the derivative of the original function, and we then get that inverse. So here we had a whole function, but let's look at a point. Since we can't, without finding the inverse, we wouldn't be able to do this. Okay. All right, so in this example, we're going to let f of x equal x to the third minus 2. And we want to find f inverse prime at x equals 6. So x equals 6 is the same thing of saying f of 2, meaning I plug in a 2 for x and I get 6. So x equals 6 is for that inverse function, but it's also f of 2 in our original function. And we clearly in the function have a point 2,6. So in f of x, we have this point 2,6. So when you flip it for the inverse, it's 6,2. So that's pretty straightforward. Okay, so we're going to solve this without finding f inverse. So if f of x is x to the third minus 2, we know the derivative. It's going to be 3x squared. Okay. And then we want to evaluate at 2. So we're going to evaluate. So this line up and down means evaluate at x equals 2. So we plug in this 2. 2 squared is 4 times 3 would be 12. And then we have our theorem. F inverse of 2 is the same thing as 1 over f prime of f inverse of 2, which equals 1/12. Right. So we evaluated at that point without finding its inverse. So that's just a cool little theorem. Let's look at some rules. Okay, so these are just derivative rules that we could use when we talk about inverses and natural logs. They all typically go together. So the derivative of ln of x is 1 over x. And we assume that x is greater than 0, so we don't have any domain problems. Okay. So if I want to do some examples, if I want to take d dx of, let's say, ln 2x. So we do 1 over 2x. But since it's not just x, we have to account for the chain rule. So counting for the chain rule, we multiply by 2, and we get 1 over x as well. So we'll see that if we take the derivative of ln, anything with just one term in x, so if it's like ln 3x, ln 4x, ln 5x, it's still 1 over x, because when we use the chain rule, it's going to cancel out. But we have to be careful with our domain. X should be positive here. Okay. Let's do another one. Let's take the derivative of ln x squared plus 3. So it's 1 over x squared plus 3. But again, we have to use the chain rule. So the chain rule here, the derivative of x squared plus 3 is 2x. So our final answer here, we'd get 2x over x squared plus 3. And we have to be careful that our x is greater than 0 as well. Or our domain follows our x is greater than 0 rule. So we'd have to find our domain separately here, so to make sure we don't have any issues. I'll leave that as an exercise. Let's look at another rule. So if we have the derivative of an exponential, so let's say we have a to the x, we get a to the x times ln a. Right? This one's pretty straightforward. So if we have the derivative of, let's say, 3 to the x, the derivative is 3 to the x, and then times ln 3. If we want a little complicated one where we have to use the chain rule, if we take the derivative of 3 sine x, we get 3 sine x times ln 3. But then we have to multiply by the derivative. Derivative of sine is cosine, so times cosine x. Let's look at one more rule. Let's say we have the derivative of log base a of x. This is 1 over x ln a. We have a few restrictions here just because it is log. So a always has to be greater than 0 with logs, and a can't be 1. So that's just back to algebra where we'd have that rule. So if we want to take the derivative of, let's say, just log base 2 of 3x, this would be equal to 1 over x in this case is 3x times ln a, so ln of 2, count for the chain rule times 3, so we have 1 over x ln 2. Okay, so that's going to be it today. I will see you in next class, and I hope everyone has a great day.